Hello everyone, welcome to this presentation on proteins. So today I'm going to discuss with you proteins, the characteristics and the structure of amino acids. Proteins are another group of biomolecules. It's a major biomolecule. Proteins have very diverse function. It does not only make your muscle big, it has many important physiological function. So proteins are um, molecules. They are polymer. Some proteins are small, some proteins are big. Okay, but proteins are made up of amino acids. Unlike carbohydrates are made up of sugar units, but proteins are made up of amino acids. Um, Proteins are built on these atoms: carbon, hydrogen, nitrogen, oxygen. Some contains sulfur. As I said earlier, amino acid is the building block of protein. So proteins are built on amino acids linked together. Okay, what's an amino acid? Amino acid is an organic compound that contains both an amino group and a carboxyl group. Okay, these two functional groups, the amino group and the carboxyl group, are attached on the same carbon atom. As you can see in this structure, this shows the general structure of amino acid. On the left side, that is an amino group, and on your right side, the right side of the carbon, you have the carboxyl group. Okay, and then it has a hydrogen atom and an R group or side chain. Okay, remember an R, it says before that this represents the rest of the molecule or any group of molecule. Okay, the R or the side chain um, vary in size, shape, charge, acidity, and functional groups present. So all amino acids, okay, all standard, I should say, all 20 standard amino acids. Those 20 standard amino acids, they only differ in the side chain, but they share the same structure. They have an alpha. This is the alpha carbon, okay, and on the alpha carbon they have the carboxyl group and they have amino group. So the 20 standard amino acid differ only on the side chain. Okay, there are 20 standard amino acids. However, there are more than 20 amino acids known. So they are called, the rest of the amino acids are called non-standard. Okay, but we will be just talking about the 20 standard amino acids. The standard or the 20 amino acids, the 20 standard amino acids are classified according to the R groups. Okay, remember R groups, these are the rest of the molecule or the side chain. So let's classify them according to the R groups. First, we have non-polar amino acids. Okay, the reason why they are non-polar because their R groups are non-polar. Say for example, alanine. Okay, the R group that is highlighted. Okay, we have what's this? Pink. The highlighted. Okay, the R group is CH3 methyl. Remember, we know that methyl CH3. That's a hydrocarbon. Remember, hydrocarbon is non-polar. Okay? Valine. Okay? Valine or short ball, and or V. Valine, the side chain or the R group is an isopropyl. Okay, this is an isopropyl. Okay, so as you notice, their R groups are all hydrocarbons. So they are non-polar. Normally, when these amino acids are present in protein, they actually are hidden. They are actually, when these non-polar amino acids are present in protein, these amino acids are hidden, usually in the center of the protein, away from the water environment. The second classification of amino acids is called polar neutral. Okay? When you say polar, when you say polar, it's due to the presence of an electronegative atom. Okay? So, example, serine. Okay? The side chain, the R group contains hydroxyl group. Okay? This is an alcohol. We know that an alcohol is polar. Okay? So, the rest, what you can see is they have an atom, they have atoms that are polar or electronegative atoms. So here there's a sulfur, there's an oxygen also, there's an alcohol. Okay, here there's an oxygen also, and there are nitrogen. So polar, so expect them to be associating with water. Okay, polar amino acids interact with water molecules, but they are neutral. That means the side chain, the R groups, are neither positive or negative. Okay, nor negative. All right. The third classification is called polar acidic. Okay, polar still due to the presence of electronegative atoms such as oxygen, but at the same time they are acidic due to the presence of carboxyl group. Okay, so aspartic acid and glutamic acid, both of them have carboxylic acid. So polar acidic. Okay, so aspartic acid, for short, ASP, single letter abbreviation D. Glutamic acid, GLU, or E. The last group of amino acids called polar basic. Again, they are hydrophilic. When we say hydrophilic, they could associate with water due to the presence of electronegative atoms such as nitrogen there. Okay, and at the same time basic, they are basic. Okay, they could participate in the acid base reaction. This basic amino acids, they could accept proton. Remember, the definition of a base is they accept proton. Okay, so the presence of the nitrogen in their side chain makes them basic. Polar, basic. Okay, example, histidine or his, H, lysine, LYS or K, arginine, ARGS, or simply R. The name of amino acids can be represented in various ways. It can be by writing the full name, or usually for long chain of protein, we rather use the three-letter abbreviation or the one letter symbol for even longer protein. For example, um, alanine. For alanine, it can only be written as ala. Okay? For glycine, it can only be written as GLY or gly. However, for even longer proteins, the three-letter abbreviation can be long. Okay, it results to a very long name of protein or chain of protein. So instead, we use a one-letter symbol. For example, W for tryptophan, R for arginine, and E for glutamic acid. And there are some more that have this nomenclature. We have learned before that a chiral center is an atom that is attached to four different groups. And when a molecule contains a chiral center, then the molecule exhibits enantiomerism. Okay? There are two forms of enantiomers, the left and right form. The L being the levo or L, the right being the D or dextro. We have learned that in the carbohydrates. Now, since the general structure of amino acid, it has a carbon, and to its right side there's a carboxyl group. Okay, and on the left side there's an amino group. Okay, and it has an R group and hydrogen. So there are four different groups. Therefore, this carbon is a chiral center. Okay. Now, since this chiral center has this carbon is chiral, then the amino acid exhibits pair of enantiomer. If the if the amino group is at the left side, okay, at the left side of the alpha carbon, okay, this is called the alpha carbon. If the amino group is at the left side of the alpha carbon, then the amino acid is designated as L. And we know that the mirror image of L is a D. Okay, so for example, when the amino acid is, let's say, valine or valine. Okay, let's draw the structure of valine. Okay, that's the amino group and it's the hydrogen. Okay, now let me draw the R group below the alpha carbon. Okay, I'm drawing alanine. Sorry, I'm drawing alanine. Okay, alanine. Because it's a smaller molecule. So alanine, okay, the R group is methyl group. Okay, it has a carboxyl group and it has an amino group at the left side of the alpha carbon. Since the amino group is at the left side of the alpha carbon, then this is designated as L-alanine. And of course, since this has a chiral center, the alpha carbon is the chiral center, then it has a mirror image. Okay? The mirror image is the D-alanine. Okay? D-alanine. Okay? How do you draw D-alanine? Okay? You just have to switch the position of the hydroxyl, the amino group and the carboxyl group. If you switch the position, if you put this amino group at the right side, then that is a D. Okay, D-alanine. So this L and D are form of enantiomerism. Okay, they are pair of enantiomer. Now, if you would ask what predominates between the two in nature, okay, it's the L amino acids that predominate in nature. They are the most most abundant or more abundant compared to the D. However, in monosaccharides, we learned before that the D form, that D enantiomers, are the more predominant form. Out of out of 20 amino acids or 20 standard amino acid, glycine, okay, glycine has no chiral center, okay, because glycine has its R group is also hydrogen, okay. That's why glycine has no pair of, okay, has no pair of enantiomer, okay. Out of 20 standard amino acid, okay, 19 amino acids exhibit enantiomerism. Okay? Okay, at this point, we will study the acid-base properties of amino acid. Let's first define, let's review the definition of acid. An acid, according to Lorry and Bronsted, an acid is a substance that donates, okay, donates proton or simply hydrogen ion, whereas a base is a substance that accepts, okay, accepts hydrogen ion. Now, an amino acid that has a formula, see, this is the carboxyl group, all right, and it has an amino group here. Let's just write the hydrogen and the R group, the general. This is the general formula of amino acid. Now, an amino acid can undergo intramolecular proton transfer. Okay? Now, we know that carboxyl group is acidic because of the presence of ionizable hydrogen. All right? Now, and we know, we learned that an amino group is a basic group or basic compound because due to the presence of lone pair of electron. So in an amino acid, there is an intramolecular, intra within, okay, a transfer of proton within the molecule. So when that happens, when the carboxyl group transfers proton to the amino group, what will happen? Okay, so when the amino group, okay, receives the proton, okay, this proton comes from the carboxyl group. When proton is transferred to the amino group, what happens is this will become NH3. Okay? Now, let's reflect this in the intramolecular proton transfer. So let me write again the structure of amino acid. All right. Now, as you notice, the amino group is H2N. I just wanted to show you the bonding between the carbon and the nitrogen. Okay? So, the hydrogen, the R group, and the carboxyl group, carboxylic acid. Okay? So, we will transfer the proton to the other side, which now becomes like this. Since we remove the proton, the carboxyl group becomes negatively charged. Okay? And since the amino group received the proton, this now becomes, okay, there are 3 hydrogens, then it's positively charged. Okay? Let's write the R group below, the hydrogen above. Okay, take note that the amino acid now is a neutral. Okay? It's neither positive nor negative. The net charge is zero because it's negative plus positive is zero. Okay, when you have an amino acid in this, when an amino acid is in this form, we call that sweeter, okay, sweeter ion. Sweeter ion, meaning um, doubly charged or two charges, the positive and the negative. Sweeter ion, the net charge is zero, where the carboxyl group is negatively charged and the amino group is positively charged. This is the sweeter ion form of amino acid. Okay, when do we attain, when does an amino acid attain a sweeter ion form? Okay, it says here, the amino acid is in sweeter ion form if it is in its isoelectric point. It says an isoelectric point is a pH at which the concentration of sweeter ion is at maximum. In other words, we can attain a sweeter ion form of amino acid if the amino acid is in its isoelectric pH. Okay? As you can see in the screen, the different amino acids have different isoelectric point, or the PI, that's isoelectric point. Okay? Isoelectric point, that's a pH where the amino acid is in sweeter ion form, or the net charge, as I said, is zero. So for example, alanine. Okay? I want alanine. Now, if you look at the table, the isoelectric point, or the PI of alanine is 6.0. Okay? At pH 6.0, alanine exists in its sweeter ion form. So, as I said, when it's in sweeter ion form, the structure of alanine would be something like this. Okay, the carboxyl group is negatively charged and the amino group is protonated or positively charged. Okay, let's draw alanine. Okay, alanine becomes like this. Okay, this is the sweeter ion form if the pH of alanine is 6.0. Okay, what is the net charge? No net charge. Okay, the net charge is rather zero. Okay, because the amino group is positive, the carboxyl group is negatively charged. How did we get, the question is, how did we get 6.0 as the isoelectric point, okay, for alanine, 6.0. All you have to do is, in this table, there is this value, okay, for alanine, the pKa1 is equal to 2.34, okay, and then the pKa2 is equal to 9.69. You get the sum of that, that's around 12.03, and then you divide that by 2, the answer is 6.01. Okay, so rounded up 6, okay, 0.0. So that's how we get the isoelectric point of amino acid. For those amino acids that are acidic and basic, we select the amino acid, or we select the pKa. Okay. So for example, aspartic acid. Aspartic acid has acidic side chain. Okay? Acidic side chain. So to get the IPH or isoelectric point of aspartic acid, we select the um, pKa 1, which is 1.88. Okay, and since the side chain of aspartic acid is acidic, then we get the pKa 3, which is 3.65. So you add the two. I don't have calculator here. You just have to try in your place. You add the two, and then whatever the result here, you divide by 2, and I hope that it will become 2.77. Okay, so this is the IPH of aspartic acid. At 2.77, okay, the aspartic acid exists in sweeter ion or sweeter ion form. Earlier, we have seen the condition in which amino acid attains its isoelectric or its sweeter ion form. So we have said that an amino acid, if it is in sweeter ion form, the net charge is 0. At what pH? When the amino acid is in its isoelectric pH. For example, in our case earlier, the isoelectric point of alanine is 6.0. At this pH, at pH 6.0, okay, at pH 6.0, alanine exists, okay, in the form of sweeter ion. The carboxyl group is negatively charged and the amino group is positively charged. Okay? So this is the sweeter ion form. The net charge is 0. Now the question is, what happens when the pH changes? When the pH changes, for example, when the pH decreases, say from 6.0, the pH decreases to, let's say, 2.5. Okay? So we know that if a pH that is 2.5, that means this is acidic. Okay? Any pH below 7, okay? Any pH below 7, okay? That is in the acidic region. Any pH above 7, that is in the basic or basicity level. So when alanine, okay, when alanine is in a pH 6.0, but if the pH of the solution or if the pH of the condition changes to 2.5, what will now the structure of alanine? Okay? Let me write again. The structure of alanine. Okay? At, what's the IPH? The IPH is 6.0. Now, the condition that I said earlier is what happens when the pH will decrease. It's either you add strong acid or any acid. When you add acid, let's say this is your container that has the alanine. Okay, initially the pH is 6.0. Okay, now if you will add an acid, okay, eventually the pH of the solution will drop or will decrease. We just don't know how many, what is the degree of decrease. But we know that upon adding acid, the pH will eventually decrease. But our concern is what is the structure, what will now be the structure of amino acid in a condition that is acidified. Okay, so we expect that the pH here is lower than 6.0 because we have already added acid. Okay, so let's write here low pH. But our concern is what is the structure of our alanine. Okay, so here we put hydrogen ion that represents acid. Okay, this is our acid. Okay, now since this is a positive, okay, our acid is positively charged, what will happen is the acid will go to the carboxyl group. Okay, so let's write that again. Now, since the carboxyl group accepted or received the proton, then we now have a protonated carboxyl group. The amino group remains positively charged. Okay, now what is the net charge of this amino acid, this alanine this time? The net charge is positive 1. Okay, so we can conclude that the charge of alanine or the net charge of alanine in the pH below its isoelectric point is positive 1. Again, the net charge of alanine below its isoelectric point is positive 1. Okay, so let's net charge positive 1. How about if the pH is higher than its isoelectric point? Okay, earlier our case was the pH was lower than its isoelectric point. So this time, how about if the pH is higher than its isoelectric point? So remember that the isoelectric point of alanine is 6.0. Now, this time, our case is the pH is above 6.0. What will now the form or the net charge of alanine? So let's begin by writing again the structure of alanine in its sweeter ion form. Okay, our reference is the sweeter ion form because that's the structure of alanine at pH 6.0. Okay, so this time we're going to increase the pH by adding a base. Okay, let's say hydroxide. Okay, remember hydroxide is basic or is a base. So since hydroxide is negatively charged, of course it will not go to the negative. Okay, but instead what happens is this acid here will go to the base. Remember, this is it has an acidic hydrogen. It's positively charged. The positively charged goes to the hydroxyl group. Okay, so when that happens, this will now become the structure of alanine. The carboxyl group remains negatively charged, okay, but the amino group this time has no positive charge anymore. Okay, because remember we have taken the positively charged here and it went to the base. So that's actually water is released. So when the positive has been, when the positively charged hydrogen went to the hydroxyl group to form water, the amino group has no charge anymore. However, the carboxyl group remains negatively charged. So, if we will ask what is the net charge of alanine at pH higher than 6.0, the net charge now becomes -1. Just like what you can see in the screen, okay? In the screen, you have a sweeter ion, okay? Net charge, net neutral charge, meaning non-net charge, the net charge is 0 rather. At high pH, okay? At high pH, by adding base, the net charge is -1. At pH lower than its isoelectric point, generally the net charge is positive charge. Okay?